Throughout my time in researching spaceflight, I've seen many people asking how a rocket functions in a vacuum with no air to push off. I've also seen many questions asking how they can operate in the absence of oxygen. It seems to me there is a misconception that, like fire, rockets require oxygen. This is not the case. To understand what's going on and why this isn't true, we must look into three aspects of rocket propellants. 1. What a rocket propellant is. 2. How they store energy. 3. How that energy is made available. Firstly, let's define what a rocket propellant is. The object of a rocket motor is to provide thrust, and it does this by ejecting a stream of gas at high velocity. The propellant is something that is consumed to produce this stream of gas. Typically, propellants fall into three categories. Today we'll be looking into liquid bipropellants. These are liquid propellants consisting of two parts, a fuel and an oxidizer. They are commonly used in commercial rockets where the fuel tends to be RP1, a kerosene derivative, liquid hydrogen, or increasingly liquid methane. As you may have noticed, they share liquid oxygen as their chosen oxidizer. This might suggest that liquid oxygen is the only possible choice. However, we know this isn't true because Bell Aircraft and Rocketdyne fired engines that use chlorine trifluoride as an oxidizer as early as 1948. This implies there is some chemical property that determines whether a compound can be used as an oxidizer. Before we figure out what that might be, let's look at how propellants store their energy. When compounds are formed, they create covalent bonds between their atoms and release energy. We can leverage this by using propellants which consume less energy when breaking the bonds than is released when forming the reaction products. In the case of liquid hydrogen and liquid oxygen, the energy is released when forming water, and that energy is greater than the amount required to break the hydrogen-hydrogen bonds and the oxygen-oxygen bonds, thus giving us a viable bipropellant. During the ensuing chemical reaction, our exhaust gases are formed and we see a transfer of electrons between the reactants. With that, we enter the realm of redox chemistry, which states that any species which loses an electron during the reaction is an oxidizer. If this sounds familiar, that's because the oxidizer of our rocket propellant is exactly that. Therefore, any chemical compound which loses electrons when it reacts with our fuel can serve as our oxidizer. Oxygen is not required. To those of you who might be asking, if any compound can be our oxidizer, why is liquid oxygen so extensively used? This is down to the properties we look for in an oxidizer. In theory, we want to maximize the mass rate flow of the gas and the exhaust velocity. In reality, rocket chemists must make a series of compromises, and liquid oxygen is consistently good across the board, rather than being exceptional in some areas and mediocre in others.